Okay, so in this video tutorial we're going to be talking about objects moving at a constant speed. So we're going to define speed and also velocity, and then just kind of hypothetically talk about when things are changing their speed. So to start things off, let's talk about the graphs that you guys got from your lab. So when you graphed your position versus time for the red and blue buggies, we saw that one of the vehicles, let's say in this case the red vehicle, and had a steeper slope than the blue vehicle. Okay, so we have the red and blue buggies represented by the red and then also blue, well, that's already blue, lines. So for both graphs, so now let's kind of look at what's going on for both of the graphs together. So the question is, what is increasing? Well, as time goes on, the distance is increasing. So the distance for both graphs is increasing. Now, what is constant for both graphs? What we discussed in class is that the slope for both individual graphs is the same at the beginning as it is in the middle. So if I do the rise over run down here for the blue buggy and I do the rise over run for the blue buggy over here, I would get the same slope. It's actually, a matter of fact, what is the definition of a linear graph. So the slope is constant for both graphs. So the next kind of natural question is, all right, well, what does that slope represent? So it's always a good idea to take a look at the units of the slope, and so it's a change in y, which would then be a centimeter over a second. So what it represents is the rate of change in distance. Okay, now when we talk about something being a rate, that means it's divided by time. So you notice that divided by seconds is in the denominator of the unit. All right, so in other words, what it represents is the speed of the two buggies. Okay, and the term that we'll be using shortly is the velocity of the buggies, and we'll talk more about that in a little bit. So from the example, what is the slope of the red buggy? Well, the red buggy goes, in 3 seconds, it goes 120 centimeters. So the slope then would be 120 over 3 seconds, 120 centimeters over 3 seconds. And that, of course, is 40 centimeters per second. Whereas the slope of the blue buggy goes the same distance, 120 centimeters, but it takes 6 seconds to do it. So the slope would then be 120 centimeters divided by 6 seconds, and that, of course, is 20 centimeters per second. So what we notice is that the blue buggy has a steeper slope, okay, which what conceptually represents is that it is going faster, and that's something that you probably picked up in your lab. Okay, and you know, whether your blue buggy went faster than your red buggy, it's really irrelevant. Just one of them was traveling faster, and when we plotted them on the same graph on top of one another, the red and blue, we saw one had a steeper slope. So let's kind of try to represent that motion in a different way. So let's suppose the red buggy was dripping red paint, and it did so at equal intervals, meaning it dripped 1 drop of paint per second, and the buggy was moving along the ground. Well, just as we kind of represented in class that if the red buggy is going at some speed and it drops this red paint, then those dots are going to be spaced out, and since it's going at a constant speed, the distance between every drip is going to be constant, regardless of whether it looks constant. But the blue buggy is going to be dripping blue paint, okay, but it's going half the speed. So that means that every drip, if it's still dripping 1 drip per second, every drip is going to be half the distance between every successive drip. So what we'll see is that, you know, in the same amount of time, so 1, 2, 3, 4, 5 seconds, 1, 2, 3, 4, 5 seconds, let's get rid of 1 here, okay, it will go half as far. Okay, so we can represent this speed by these drips, okay, and we'll talk more about that in a bit. All right, so what if the buggy was increasing its speed at a constant rate? So notice that the distance between every successive drip is equal, meaning that it's moving at that constant speed. So now we're kind of flipping the question is, well, what happens if it's not if it's not traveling at a constant speed? What happens if it's increasing that speed? Well, as you might imagine, if it's increasing its speed, it's increasing the distance between every successive drip. So these distances are getting bigger as time goes on. Here, in that 1 second, it traveled that far, being faster, and here in that 1 second, it traveled that far. So then the next logical question is, all right, well, what would happen if it's slowing down? Well, if it's slowing down, right, we would expect it to decrease its distance between every drip. So let's say it's going fast at first, so kind of the reverse of the previous example. If it's going fast at first, and then as it slows down, the distance between every drip gets smaller and smaller. So in this last second of time, it traveled less distance than in the first second, which is the definition of going at a slower speed. So the next thing is, what are some other scenarios? We talked about 2 other scenarios in the dripping paint, but what else can we do, and how does that change the graph? So let's imagine the car going backwards. So if this blue line represented the car going forward, it's starting off at a position of 0 at a time of 0. What would we expect it to look like if it was going backwards? Well, let's say instead of starting at a position of 0, a distance of 0, let's say we start at that distance of 120. Right? And now we're going to head back to 0. But I'm not just going to be able to do that instantly. It's going to take some time in order for that to happen. Let's say, it takes, 5 seconds. It takes me 5 seconds to get back to a distance of 0. So what I will see, instead of it having a positive linear slope, I will have a negative linear slope. Okay, meaning that my speed is still constant. So if I find the slope here and I find the slope there, my slope stays the same, but it's just we have a negative slope. So we have, by definition, what we call a negative velocity, which just means, in our simplest case, it's going at some speed in the opposite direction that we choose to be positive. Well, what would it look like if it's increasing its speed? So you can imagine if a linear plot is representing something going at a constant speed, then we know that we're going to introduce some type of curve. And remember from before that the steepness of the graph represents the speed. So if something's getting faster, the graph is going to get steeper. So if the graph is going to get steeper, then what we would see is something that is curving up, looking like a quadratic. Now, the way that we can kind of quantify this is drawing in a tangent line. So from your math class, right, a tangent is something that is perpendicular to the radius at a particular point. So a tangent line here might look like that. A tangent line here might look like that. And a tangent line at the end here might look like so. So if I look at the steepness of these tangent lines, I see that the tangent line is getting steeper as time goes on, representing that the speed is getting bigger as time goes on. So what would happen if we reverse that? Let's decrease the speed. Well, in order to decrease the speed, we have to start off moving fast, which means we have to start off with a steep slope. And then over time, that slope is going to get smaller. So instead of it's something that curves up, we might see something that curves down, kind of like a square root graph. And if I draw in some tangent lines there, in the beginning the slope is very steep, in the middle it's getting less steep, and at the end it's getting close to a zero slope, which would just mean that the object is no longer moving. Okay, so slope gets steeper, increasing our speed. Slope gets less steep, decreasing our speed. So what are the equations for these graphs? Well, what we said is that, and we can kind of help with the units here, that the slope of this graph represents, it's actually the definition of velocity or speed. So the slope, it represents a change in distance over a change in time. Okay? And generally, we drop this delta because we have an initial time of 0. So generally, you'll see this in your reference tables, that even though it is a change in time, it's implied that it's a change in time, generally we'll just write it as t. So it's a change in distance over a change in time, so that's our definition of our slope. But we can also kind of get there from the y equals mx plus b equation. Because this graph, although it being negative, is a linear graph, so we can describe it with this y equals mx plus b, and maybe it's easier to kind of reference the graph up here. So we have distance on our y-axis, so where we see y, we're going to put a d. We have time on our x-axis, and we said the slope represents the speed. So we can write this as distance equals some speed times time, and then our y-intercept is basically read as the distance at a time of 0, meaning it's our starting distance. Okay, what we'll eventually call an initial distance. So I'm going to write it as di. Okay, so d sub I. This is our starting position. Now, most of the time, this is 0. Okay, so if this is 0, then you can cancel that out. But you could see something like this. Our starting distance is at 120 centimeters. Our starting position, 120 centimeters. And I'll leave this up to you, but basically if you take this original equation, okay, solve this for d, you'll notice that you get this expression right here. I mean, for without having this initial distance. But if you rearrange this for t, we can get another useful expression, and I'll leave the algebra steps up to you, but the t is equal to the change in distance over that speed. Okay, now this speed actually happens to be an average speed, and we'll talk more about that in class. So the symbol we use for average, just like you've used in your math classes, like x bar, is read as v bar, and this represents average. So this is your average speed. All right, so let's look at some pretty basic examples. So if we have a blue buggy that's rolling for 9 seconds, how far did it travel? So we know a time is equal to 9 seconds, and we know the blue buggy, its speed was 20 centimeters per second. Now your numbers might be slightly different from your lab, but let's assume it's 20 from the graph above. So how far it would travel, is a distance, and so that distance is that speed times time. So we get 20 centimeters per second times 9 seconds. So that is 9 times 20, we get 180. Okay, now unit-wise, we get a centimeter per second times a second. What we see is actually the seconds cancel out, and we're left with just a unit of centimeters, which is a good thing. Distances are measured in centimeters. Now, if we want to know how much time it would take to go the 240 centimeters, we're looking for time, so we can use that third equation from above, that the time is equal to the distance it travels divided by the average speed. So if we want to know how long it takes to go 240 centimeters, and it's traveling at 20 centimeters per second, we have 240 over 20. What we end up getting is what? 12 seconds. And I'll leave this for you to work out, but a centimeter over a centimeter per second, the seconds cancel out and we're left with just seconds. So try out this last example and come to class ready to talk about it. Thanks for listening. Have a good night. Bye-bye.